3I/Atlas has already surprised scientists once, not with its arrival, but with its chemistry. Detected by the Atlas survey in July 2025, this interstellar comet is not just rare, it's weird. Most comets don't start venting gases until they're much closer to the Sun, but 3I/Atlas began releasing carbon dioxide and water vapor while still nearly 3 AU away. If you're still watching, subscribe now. You crave more than answers, you seek what lies beyond. Subscribe now and be part of the few who never stop searching. That early activity defies expectations and hints at a deep freeze origin, far colder and chemically distinct from anything born in our solar system. And with perihelion just days away, astronomers are watching closely. What it does next, whether it brightens, breaks apart, or holds together, could rewrite what we know about how planetary systems form. This isn't just about one comet, it's about the story it tells. 3I/Atlas, like Oumuamua and Borisov before it, is a visitor from another star, carrying clues about where and how it was made. Spectra, dust patterns, volatile emissions, they all suggest it came from the outskirts of a foreign protoplanetary disk, formed in conditions unlike any we've seen up close. As observatories including JWST prepare to analyze its next moves, this brief encounter could open a new window into how material moves between star systems and how those exchanges shape planets, comets, and maybe even life itself. It's not from here, it doesn't behave like anything from here, and now, it's heading straight for the Sun. This is 3I/Atlas, an interstellar visitor with a signature we've never seen before. It passed Mars, it's closing in on its closest approach to the Sun, and something's off. First discovered in July 2025 by the Atlas survey in Hawaii, 3I/Atlas became only the third confirmed interstellar object ever detected passing through our solar system. The first was Oumuamua, the second, Borisov. Both were strange, but this one's different. Different in ways that don't just challenge our models, they might rewrite them. Its trajectory is hyperbolic, not elliptical. That's the first clue. It's not orbiting the Sun, it's passing by it, once. From outside, that alone confirms its origin beyond our solar system. This object isn't part of our cosmic family, it's a wanderer, a relic from another star system. A probe of natural origin, carrying information about a place we'll never visit, and already it's broken the rules. At about 2.9 astronomical units from the Sun, roughly the distance between Mars and Jupiter, 3I/Atlas began venting gas, a lot of it. Water vapor, carbon dioxide, early intense outgassing. That's not normal. Typical comets from the outer solar system don't begin showing activity like that until they get much closer to the Sun. Heat drives that process. But 3I/Atlas didn't wait. It started shedding material far too early, too aggressively. That implies something fundamental about its makeup. It formed under different conditions, in a colder, more volatile-rich environment than any comet we've studied up close. The dominant volatile isn't water, it's carbon dioxide. That's critical. Water ice is common in solar system comets. Coals is present, yes, but usually in lower quantities and released later in the approach. Not with this object. In 3I/Atlas, 2Is are peaceably leading the charge. That tells scientists something profound. This body likely formed in a much colder region than our own Kuiper belt or Oort cloud. It could have originated in the outermost reaches of a protoplanetary disk around a star very different from our own, and it gets stranger. Spectroscopic readings show chemical signatures that don't align with what we expect. The dust it's releasing, its structure, how it scatters light, points to materials we haven't seen in this combination before. It's chemically distinct, physically different, dust grains behaving in unexpected ways, light polarization that doesn't match the models. Everything about it hints at a system with different chemistry, different temperatures, different evolutionary pathways. This isn't just a comet, it's a sample return mission from another star system, one that cost nothing to launch, and arrived on time, and now it's approaching a critical moment. On October 29, 2025, 3I/Atlas will reach perihelion, its closest point to the Sun, just 0.53 AU, that's inside the orbit of Venus. Hot, hostile, unforgiving. What happens next? No one can say for sure. There are scenarios on the table. It could flare in brightness. It could shed more gas and dust. activity could spike as solar heat hits fresh surface layers, or it could fall apart. Fragmentation is a real possibility. The stress from solar radiation, tidal forces, and internal pressure could crack it open. That's what happened to some previous comets. Comet Isen, for example, never made it past its close solar approach. It disintegrated. If 3I/8LAS breaks up, that tells us something important about the structural integrity of these interstellar bodies. Are they fragile? Porous? Are they held together by weak cohesive forces? That matters, because one day we might want to visit one. If it survives, we learn something else. We learn how these objects behave under extreme heating after traveling through the deep freeze of interstellar space. We see how volatile compounds react, how the coma evolves, how its chemistry changes under sunlight. That data can feed directly into our understanding of cometary evolution, not just here but across planetary systems. And this isn't guesswork. Observatories around the world, and above it, are locked in. The James Webb Space Telescope, ground-based spectrographs, polarization instruments, infrared and visible light telescopes, all are tracking 3I/8LAS in real time, not just to watch. To learn, this is a rare opportunity. A sample from another solar system, actively changing before our eyes, moving fast, coming close, showing us what it's made of. What's already clear is this: our models weren't ready. The early activity of 3I/8LAS, driven by CO pod, and not just water, rewrites the thresholds we thought mattered. Until now, the standard theory was that water vapor drove most activity in comets within the solar system, with carbon-based volatiles playing supporting roles. That might not apply anymore. Interstellar comets may operate by different rules entirely. This also shifts how we think about formation environments. A body like this didn't form where it's warm. It formed far out, in the coldest reaches of its system, possibly beyond the equivalent of its own Kuiper belt, a zone rich in CO pod, methane and ammonia. The chemical fingerprints we're seeing, low-temperature volatiles, non-solar abundances, point toward a birth environment that looks nothing like ours. And yet here it is. A frozen emissary from a long-lost system passing through our skies, outgassing its history. It raises broader questions too. If 3I/8LAS, Oumuamua, and Borisov are any indication, interstellar material exchange might be more common than we thought. Material ejected during planetary formation, kicked out during orbital chaos, sent drifting through the galaxy. Some of it finds its way to us. This is galactic recycling. Planetary systems exchanging fragments across light years, and with each new object, we get a clearer picture of what's out there, what kinds of systems exist, how they evolve, and how connected the galaxy might truly be. It's no longer just theory, we're observing it directly. 3I/8LAS may not be the last, but right now, it's the best look we've got. As it reaches perihelion, we'll be watching, not just for fireworks, but for answers. Will it hold together? Will its activity explode under solar pressure? Will new compounds emerge? Will it brighten or break? Whatever happens on October 29th, the data it provides will feed into everything: models of comet behavior, theories of solar system formation, plans for future missions, missions that may one day target objects like this deliberately. Because make no mistake, this is a turning point. The solar system is not isolated. We are part of a galactic network of material flows. 3I/8LAS is proof. It is a challenge. And it is an opportunity. The more we learn from it, the more we understand about where we came from, and how unique or not our system really is. If you want to keep following the journey of 3I/8LAS and what it's telling us about our place in the galaxy, subscribe. Share this with someone who still thinks comets are just dirty snowballs. And let us know what you think 3I/8LAS will do next in the comments, because something's off about this one. And we're just getting started. There's a growing sense in the astronomical community, subtle, unspoken, that 3I/8LAS may not be playing by the rules because it never learned them. Born in an alien environment, far beyond our own system's coldest frontiers, this comet doesn't just act strange, it is strange. And that strangeness is the point. This object didn't evolve under the gravitational tyranny of our sun. It was sculpted by different forces. It witnessed the birth of another star. It froze in place under different chemistry. It drifted through lightless space for possibly millions of years before fate threw it across our path. And now that it's here, Every molecule it sheds is telling a story. We're not just watching a comet, we're reading a galactic time capsule in real time. You can't overstate how rare this opportunity is. With only 2 prior interstellar objects ever confirmed, Oumuamua in 2017, Borisov in 2019, this is still a brand new field. With Oumuamua, we got a mystery. It never formed a coma. It reflected sunlight like polished metal. It changed trajectory without explanation. We still don't fully understand it. Borisov, on the other hand, looked more familiar, active tail forming, like a typical comet, but even then, its composition was off. High levels of carbon monoxide, an extreme dust-to-gas ratio, hints that it had come from a system colder, darker, more volatile rich than ours. Now comes 3I/8LES, and it's bridging the gap, active like Borisov, mysterious like Oumuamua, but more aggressive, more vocal, and potentially more revealing. Its outgassing began at 2.9 AUA, a distance where most comets are still inert. That's not just early, that's anomalous. And the nature of those emissions, dominated by CO port, throws a wrench into the entire standard model. We used to think we understood how comets behave as they approach the sun. We thought we could predict their light curves, their gas outputs, their structural limits. But interstellar comets are wild cards. They were forged under foreign conditions, with unfamiliar ratios of volatiles and refractories. Their surfaces could be coated in ices that never formed in our solar system. Their cores might be riddled with compounds we've never seen. If 3I/8LES survives perihelion intact, it will give us unprecedented insight into the stability of interstellar bodies. If it fractures, we'll learn something equally important, that these relics are brittle, built to float through frigid voids, not endure solar onslaughts. Either way, we win. Because it's not just about the object, it's about the pattern. With 3 confirmed interstellar objects in just 8 years, the old assumption that these things were once-in-a-century discoveries is fading fast. The data suggests we've only just begun to see what's out there. That changes the game. Detection systems are improving, survey telescopes are becoming more sensitive. We're no longer blind to these fast-moving hyperbolic visitors. With projects like the Vera Rubin Observatory coming online soon, we'll detect more, many more. 3I/8LES isn't an outlier. It's a representative of a new category of cosmic knowledge, a trigger for better questions. What do interstellar objects really tell us about their home systems? How common are CO port-dominated comets? Do their trajectories suggest certain regions of the galaxy are more likely to eject bodies? Could we backtrack these objects, map their flight paths through stellar drift, and one day identify their stars of origin? And further, could we intercept one? Because that's where this leads. The more we understand these objects, the more tempting they become as mission targets. Robotic probes, sample returns, maybe even crewed missions in the far future. Because no observatory, no telescope, can match the value of physically touching a relic from another world. 3I/8LES won't be the one we reach. It's moving too fast, passing too briefly. But the data it provides will guide the strategy for those that follow. Already scientists are modeling how 3I/8LES reacts to solar radiation, how its coma develops, how its trajectory shifts as gases jet from beneath its surface. These aren't just observational curiosities, they're benchmarks. If future missions are to rendezvous with interstellar objects, we need to know how they behave under solar stress. Do they break apart easily? Do they flare unpredictably? Do they spin? Do they tumble? Every answer matters. There's also the question of isotopes, specifically, the ratios of hydrogen and deuterium in water vapor. These measurements, if obtained, can tell us how water formed in other systems, whether conditions were similar to those in the early solar system, whether the materials that formed Earth's oceans could be common or unique. That's the real value here. 3I/8LES is a scientific mirror, not just telling us about where it came from, but forcing us to reflect on where we came from too. And as it nears the sun, all eyes are on it. The James Webb Space Telescope will focus its powerful infrared instruments on the comet's coma. Ground-based observatories will track its spectral lines. Analysts will watch for rotational changes, brightness spikes, or structural shifts. Because we're not just trying to catalog this object, we're trying to understand how interstellar bodies behave when subjected to solar forces, and if it survives perihelion, we'll have a long tail of data to analyze. Post-perihelion observations will be critical. The comet will recede from the Sun, gradually cooling, its activity declining. But its trail, its debris field, could be studied for months. Scientists will analyze dust particle sizes, gas-to-dust ratios, the evolution of the comet's shape. Every variable is a clue, and the more clues we gather, the closer we get to solving the puzzle of planetary formation across the galaxy. Because this isn't just a study of a single object, it's a test case for a cosmic process. Star systems don't form in isolation. They form in clusters, dense chaotic nurseries filled with gas, dust and gravitational interactions. In those first violent millions of years, objects are flung outward, some collide, some fall inward, some escape entirely. 3I/8LES is one of the escapees, ejected from its home system, perhaps by a gas giant, perhaps by close stellar encounters. It's been drifting through interstellar space, untouched, unchanged, ever since, until now, and what it brings with it is perspective. The solar system isn't a sealed vault, it's porous, connected, vulnerable. The galaxy is littered with debris from a billion formation stories, and now we know, some of it finds its way to us. That has implications, big ones. If materials can drift between star systems, so can more than just rocks. Organic compounds, amino acids, maybe even the precursors to life. It opens the door slightly to panspermia theories. It forces us to rethink isolationist models of planetary evolution. We used to think we were locked inside a single self-contained system. Now we know we're part of a galactic neighborhood. And objects like 3I/8LES are the messengers. Right now, it's burning toward the Sun, fast, unpredictable. Its chemistry shedding light on how different and how similar other systems might be. Its presence a reminder that we are not alone in our formation history. October 29th is the inflection point. We'll see what it does when it hits solar proximity. We'll watch for signs of stress, cracking, splitting, acceleration from gas jets. We'll study the light curves, measure the spectroscopic shifts, and match the emissions to volatile species. And whatever happens, the lessons will outlive the object. Because after perihelion, 3I/8LES is gone. It will swing past the Sun and continue its journey outward, upward, away, forever. It won't loop back. It won't slow down. It will vanish into the blackness between stars, a one-time visitor from a place we may never know. What we record now, what we understand in these final days, is all we'll ever get. And that makes every frame, every spectrum, every data point matter. Here's what no one wants to say out loud, but everyone's thinking. We don't understand these things. We thought we had a grip on cometary behavior. We built models. We tested them against dozens, hundreds of solar system comets. We refined thresholds for activity. We predicted gas release patterns. We thought we could tell how icy bodies respond to sunlight. And then 3I/8LES showed up. And it didn't care. It started venting carbon dioxide long before it was supposed to. It shed water vapor far beyond where water ice is normally active. Its coma is denser than expected. Its dust reflects light in strange, inconsistent ways. The spectral lines don't match the templates. It's a stubborn reminder that our understanding of comet physics is still provincial, built on a sample size that until recently never included objects born under another star. But now we have one, and the clock is ticking. In a matter of days, 3I/8LES will plunge into solar proximity. It's moving fast. Its velocity isn't governed by solar orbit, but by the deep momentum of interstellar drift. It will graze the inner edge of the solar system, whip around the Sun, and launch outward on an escape trajectory that will never bring it back. This is a one-shot encounter. And what we're seeing already tells us we're just scratching the surface. Every molecule of gas it emits carries a signature, a ratio, a chemical fingerprint from the environment where it formed. Not just the cold, but the composition of the disk, the radiation environment, The elemental inventory. This is alien geology on display. The presence of so much carbon dioxide, especially at distance, suggests that 3I/8 formed in a zone much further from its star than we usually associate with comet formation, possibly beyond the ice line of its own system, far enough out that only the most volatile compounds could condense and stay frozen. And now, as it approaches our sun, those volatiles are waking up. This isn't a dirty snowball, it's a pressurized canister of chemical history, venting under solar stress, unraveling its internal structure, and flashing signs of strain. Whether it shatters or survives, it changes the game. If it breaks apart, we get fragmentation data, how these bodies behave under thermal and tidal stress. If it holds together, we learn how interstellar structure compares to solar system integrity. In both cases, we refine our models. This is the new frontier of planetary science, fast-moving, fleeting, and unforgiving. There are no second chances, no orbital revisits. Every observation counts, and maybe that's the point. 3I/8 wasn't sent here, but its arrival is a message, not from intelligent life, but from the chaotic process that builds worlds, ejects them, and sends their remnants drifting across the stars. It's a message we only get once, and now it's burning toward the sun. Don't look away.